In the last lesson, I talked about acetic acid and the fact that if you add some acetic acid to water, it doesn't all dissociate. That is, you don't get as much hydronium ion produced as acetic acid was added. You get far less. And I said that this depends upon something called an equilibrium constant with a Ka. Well, what are equilibria? Simply put, if you have a reactant, and we'll call our reactant substance A, pen to work here, you have substance A reacting with substance B, and there is an equilibrium to this reaction which produces C and D, then this says that the reaction does not go to completion. What says that? Well, this two-way arrow right here. Sometimes you'll see this as an arrow, something like that. If the software that an instructor is using isn't adequate, they'll draw it that way. But it's best drawn with these two arrows. The forward arrow means the reaction going forward. The reverse arrow means the reaction going backwards. Well, this is actually the case with many chemical reactions. Many chemical reactions don't go to completion. And in fact, if you let a reaction go as far as it's going to go, so let's take the acetic acid, and you react acetic acid with water, you're going to get the acetate ion, and you're going to get the hydronium ion. At equilibrium, some of the acetic acid is dissociating to form acetate ion, and some of the water is reacting with that acetic acid to form hydronium ion. But at the same time, some of the acetate ion that's in solution is reacting with the hydronium ion solution and reforming water and reforming acetic acid. And in fact, the rate of the reaction, rate forward and rate backward, are the same. Sometimes this is rate 1, rate 2, it's written that way. But these rates are the same. So just as fast as product is forming, product is unforming, and reactant is being recreated. That is a state of equilibrium. It's dynamic. That is, although the concentrations remain constant once equilibrium is reached, different molecules are reacting with each other all the time. So if we were able to somehow track one particular acetate ion in solution, we'd see that sometimes that acetate ion is not an acetate ion, it's an acetic acid molecule because it picked up a proton. Then again, later on, it might react with water and reform an acetate ion if we were to track it. Similarly with the water molecules, some are forming hydronium ions as they pick up protons, and some hydronium ions are reacting with acetate ion and reproducing the acetic acid molecule. Definition of equilibrium is that the rate forward equals the rate backwards. And when you learn about equilibrium, you'll see that many factors can contribute to an equilibrium, such as temperature, pressure, etc., depending upon the reactants. But that is a completely different lesson altogether, and that's where you get into Le Chatelier's principles and so on. But all we're going to touch on is how can we treat this mathematically. That also is covered in those sections where you get into Le Chatelier's principles, and there you discuss something called the equilibrium constant. So let's talk about the equilibrium constant. Let's actually generate one for a couple of reactions. So if you've got, get my pen back. if you have 2A reacting with B to produce C plus 2D, and these things are all in the same state, and none of them are solid, none of them are liquid. Let's make them all aqueous. Then the equilibrium constant, the mathematical treatment of this, depends upon their concentrations at equilibrium. So you let the reaction go as far forward as it's going to go, and you're now at that state where the reverse reaction is happening just as fast as the forward reaction. So rate 1, rate 2, rate forward, rate backwards, they're equal. Well, the equilibrium constant is equal to the concentration of C, and we represent concentration with square brackets, times the concentration of D squared divided by the concentration of A squared times the concentration of B. Now, this squared for A comes from the coefficient. If this coefficient was 3, this would be A cubed. If this coefficient was 1, it would simply be concentration of A. See, B actually has a coefficient, you just don't see it. The coefficient for for B is 1. And the concentration for C is 1. 1 times something is that thing, so they're not shown. So really, concentration of C is to the 1 and concentration of B is to the 1. But something to the 1 is that thing. So 2 to the 1 is 2. 3 to the 1 is 3, etc. So that's the rule. You take the concentrations of the products, the coefficients become exponents. Each one of them is expressed as a concentration. Sometimes, you'll learn this when you do more on the Equilibria and Le Chatelier's principle, we'll use pressures, and then it becomes Kp instead of Ka or Kc. Your teacher may refer to it as Kc. That's the concentration constant. But in acid-base chemistry, we call it Ka, and that's for acid dissociation constant. But it's the same thing and it's built the same way. So let's look at a real example. Let's go back to that acetic acid we discussed in that earlier lesson. Just for consistency. And we're going to do something called an ice table. And you've seen these before, no doubt, but a little bit of review doesn't hurt. Okay, if we start with acetic acid in water, so that'd be aqueous, and of course water is present, and it's a pure liquid. We obtain an equilibrium wherein we have the acetate ion in solution and we have the protonated water or hydronium ion also in solution. Now, according to the rules of equilibrium, a pure liquid or a pure solid, neither of those will occur in the equilibrium expression. They won't appear in the equilibrium expression. Just these species in the same state, the aqueous species, so the acetic acid, the acetate ion, and the hydronium ion. So typically with these ice tables, what I do is I just kind of scribble out underneath the liquid water to show those values need not be considered. Now we're going to be given a scenario here, and in that scenario, you are told you have a 1 molar solution of acetic acid. And you're asked what is the pH? At equilibrium. Well, to approach this, we consider what is the starting conditions, what are the final conditions, and we also consider what is the change. So the initial conditions, that's what this I stands for in an ice table. C stands for change, and E stands for your equilibrium state, or how things are once it all reaches equilibrium. Well, we have some information here. We're told that it's a 1 molar solution. So that's our starting concentration. That's our initial. So we're going to say that the acetic acid is 1.0 molar. What this means is that if you were given a liter of water and you added 1 mole of acetic acid to it, you would have a 1.0 molar solution. Well, if you took half of that liter and examined it, so you dump out 500 mils of that into a beaker, you still have a 1 molar solution. It's still 1 mole of acetic acid for every liter. It's just you have less than a liter. So our starting condition is 1 molar. Now, at the start, we pretend that nothing has happened. So it's as though you just dumped some acetic acid into 1 liter of water, and it hasn't had time to react at all. So if it hasn't had time to react at all, then initially you don't have either acetate ion or hydronium ion present. But shortly after you pour it in, or shortly after you add it, say you're adding a solid, some of it is going to react. Well, how much? We don't know how much. So what do we do when we don't know how much? We use X or Y or some variable. It's going to change by some amount, and it's going to change to the negative. That is, the amount is going to decrease. There's going to be less acetic acid and more acetate ion and more hydronium ion, because these will form. How do they form? They form from this. So some of this must be consumed. So it's a negative value, minus X. But these increase in concentration. So they're a positive value. And how much do they change? They change by the same amount. Well, how do I know that? I know that because of the coefficients. For every 1 acetic acid, you get 1 acetate ion and 1 hydronium ion. So if this changes by negative X, this has got to change by plus X, also plus X. You can think of this as negative 1X and plus 1X and plus 1X. You get 1 of each of these for every one of those that reacts. So what do you have at equilibrium? Well, at equilibrium, you just add those two lines together. You have 1.0 minus X. You have X. And you have X. Well, your ice table is done. The next step is, well, what do you do with the ice table? Well, using the ice table, we're going to calculate the value of X. Why? We're going to calculate the value of X because X is hydronium ion concentration at equilibrium. So we're going to calculate X. Value X at equilibrium using equilibrium expression. So we're going to calculate X. Well, how do we do that? We use the equilibrium expression. The equilibrium expression is what I showed earlier that we create based upon the balanced chemical equation. So in our balanced chemical equation, we have 2 products and 1 reactant, and the 2 products, so we've got K, get that pen working here, we've got Ka equal to the concentration of the acetate ion, it's the 1 product, times the concentration of the hydronium ion, that's the 2nd product, all divided by our reactant, concentration. And remember, these are all equilibrium concentrations. So we started with 1 molar acetic acid, but using our ice table, we found that at equilibrium, we didn't have 1 molar, we had 1 molar minus X. And acetate ion, we started with 0 in solution, but at equilibrium, you had plus X in solution. And hydronium, you had plus X in solution. So here we can substitute those. We can say that we have X times X over 1.0 minus X. So we've taken our concentration values and we've replaced them with these variables and these numbers. Well, what about K? K, we're going to look up Ka for this acid. For acetic acid, Ka is 1.8 times 10 to the minus 5. So Ka equals X times X, which is X squared, over 1.0 minus X. Well, to solve this equation, you multiply both sides of this equation by 1.0 minus X. So that would be times 1.0 minus X up here. And you do the same to this side of the equation. Multiply 1.8 times 10 to the minus 5 times 1.0 minus X. And I'm just going to work that through without showing all the math. So Ka equals 1.8 times 10 to the minus 5. That's 1.8 times 10 to the minus 5 times 1. Minus 1.8 times 10 to the minus 5x. And all of that, excuse me, equals X squared. Okay, so this side of the equation equals X squared, and we want to get this equal to 0. So we want to bring everything on this side of the equation over to the other side of the equation. And when we do that, we get X squared plus 1.8 times 10 to the minus 5 X minus 1.8 times 10 to the minus 5 equals 0. We now have a quadratic equation which can be put into the quadratic formula to solve for X. X equals some number. Well, what is X? If you get, I haven't worked this calculation out yet, but if you get X equals, 1 times 10 to the minus 6. What is X? Well, you look back at your ice table and you'll see that X actually is the concentration of hydronium ion at equilibrium. It's also the concentration of the acetate ion at equilibrium. But the important thing is X equals the concentration of the hydronium ion. Whatever number you come up with, we have the pH is equal to the negative log of the hydronium ion concentration at equilibrium. And you're going to get some pH, which is probably somewhere around pH 2 or pH 3. Well, thanks for watching this video. The next video in the lesson will look at acid-base chemistry equilibria in a little bit more detail, and we will address a few more difficult problems using ice tables. Some of those scenarios will include calculating the starting concentration if given a final pH.